So our question is to determine the internal resistance of a given primary cell using potentiometer. So this is also one of the most important questions in your physics textbook. So in the previous class already we had discussed about the using potentiometer to compare the EMFs of the two cells. But in this class, using potentiometer, we can determine the internal resistance of a given primary cell. So already I told you. So the potentiometer is used to measure the EMF of a cell or potential difference between the 2 points accurately. So already I told in the last class. Okay. So and the working principle of the potentiometer. So working principle. What is the working principle? Working principle of potentiometer. So the potential drop across any portion. The potential drop across any portion of the wire is directly proportional to the length of the wire, length of the portion of the wire or length of the wire. Okay. So the potential drop across any portion of the wire is directly proportional to its length. If the length is increases, the potential drop is also increases. If the length is decreases, the potential drop is also decreases. So this is the working principle of potentiometer already. So we had discussed about the potentiometer working principle and potentiometer uses in the previous class. So you can once check it out. So now our task is using this potentiometer we can determine the internal resistance of a given cell. So for that purpose, so we can draw a potentiometer here. To reduce the length of the potentiometer, length of this operator, so we can cut the conducting wire to equal pieces, and those equal pieces are connected to the strips. These broad lines are strips. So we can connect the wire, equal length wires are connected to these strips like this. So here this is called point A and this is called point C. So from A to C, that is conducting wire. Conducting wire can be equally cutted and the wire will be so connected to the strips. So looking in the diagram. Okay. So now we can connect. The symbol is represents high resistance battery. So high resistance battery, and we can connect a variable resistor, and here we can provide a key K1. So already we draw the diagram in the previous class, but so here there is a small little bit change in the circuit diagram. So here this is the potentiometer diagram. Here from A to C, the right side portion is called secondary portion and the left side one is the primary circuit, and the right side one is the from A to C, it is the secondary circuit. So in a primary circuit, so we can provide a battery to the potentiometer and a variable resistance or rheostat to the potentiometer, and we can provide a key K1 to the potentiometer. So here our task is to measure the internal resistance of a given primary cell. So that's why here we can connect the only one cell, given cell. We can connect the cell of EMF E. We can connect the cell of EMF E. So we can connect whatever the cell. So we need to determine the internal resistance. So that cell is connected here. So only one cell, given cell is connected to here, and a resistance box is also connected to the circuit through a key K2, switch through a key K2. So here here the given primary cell is connected. So we need to now we need to calculate the internal resistance of this cell. So the cell is connected and a resistance box is also connected, and that resistance box is connected through a key K2 to the point A. So now this entire so the entire circuit is connected through a galvanometer, and the jockey is provided. The jockey is provided. Jockey. The jockey is provided. So jockey is looking like a screwdriver. Screwdriver. Just we can use it. The jockey is to slide over on the wire from A to C. A to C. So the same process in the previous class. The same process will be again repeat here. So initially the key K2 is opened. Key K2 initially key K2 is opened. Key K2 is opened. So whenever the key K2 is opened, the battery does not connected to the circuit. Battery does not connected to the connected to the circuit. So that's why no current is drawn from the battery. So whenever the key K2 is opened, only the key K1 is closed. So the battery does not connected to the circuit and no current is drawn from the battery. Okay, so that's why, so whenever the battery is not connected to the circuit, that means the battery is in open circuit, and if the battery, no current is drawn from the battery, then the battery has maximum potential difference. Already we discussed it. So that maximum potential difference is called as the EMF. Okay. So that EMF E is equal to phi L1. That EMF is equal to phi L1. So why? Because so whenever the key K2 is opened, so the battery does not connected to the circuit, and that's why the battery does not provide any current to the circuit, and we can slide over the jockey. We can slide over the jockey from A to some point, then some point N1, A to some point N1. So at some point N1, the galvanometer shows null deflection. So then we said that the circuit is balanced. So now we can write according to the Kirchhoff loop rule. So EMF of the battery is equal to phi L1. So here L1 is what? The length of the AN1 can be is equal to L1. So the length of the AN1 is equal to L1. So at point N1, so we can move the jockey. We can move the jockey away from the point A. So we can slide over on the wire from point A. So gradually we can move away from the point A. The galvanometer potential difference drops gradually. So at point N1, the potential difference is drops to 0 in the galvanometer. So here what is the phi? Phi is potential drop per unit length. Phi is potential drop per unit length. Potential drop per unit. So phi is called potential drop per unit length. So therefore now we can close the key K2. We can close the key K2. So key K2, now key K2 is closed. Key K2 is closed. So whenever we close the key K2, then the battery is connected to the circuit and some current is drawn from the current battery. So some current is drawn from the cell. So whenever the key K2 is closed, the battery is connected to the circuit and some current is drawn from the battery or cell. So now the cell doesn't have the maximum potential difference at its terminals. So now we can say that it has only potential difference. We can't say that it is a EMF. Why? Because some current is drawn. It doesn't have the maximum potential difference. Why? Because some current is drawn from the cell. So that's why now the cell has only potential. So now the potential difference of the cell V is equal to phi L2. The potential difference of the cell V equal to phi L2. So how we get V equal to phi L2? So when the key K2 is closed and the cell is connected to the circuit and some current is drawn from the circuit, and again we can slide over the jockey on the wire. We can slide over the jockey on the wire from point A to point C. At some point N2, the galvanometer shows null deflection. So now the AN2 length can be taken as L2. So now the potential of the cell is equal to the phi L2. So where AN2 length can be considered as L2. So whenever the cell is not connected to the circuit, we get EMF equal to phi L1. Whenever the cell is connected to the circuit, so we get potential V equal to phi L2. So we get two equations from the circuit diagram. So now equation 1 by equation 2, from equations 1 and 2. So from equations 1 and 2, so how we can write equations 1 and 2? So E by V is equal to so L1 by L2. So E by V equal to L1 by L2. Why? Because phi is what? Potential drop per unit length. Phi is what? Potential drop per unit length. So phi cancel. So finally, so what we get? EMF by potential, E by V equal to L1 by L2 from equations 1 and 2. So but already we know that EMF equal to I of R plus R and V equal to IR. So already so we knew that. So at the starting of this lesson, current electricity, so the EMF is equal to I current into R, small r, internal resistance plus capital R, external resistance. So EMF equal to I of small r plus capital R. And according to Ohm's law, already we knew that Ohm's law, according to Ohm's law, potential V is equal to I into R. I means current, R is the resistance. So now these two values are substituted in this equation. So what we get? So I of R plus capital R by IR is equal to L1 by L2. So here I cancel. Here I cancel. So finally what we get? Smaller. If we simplify this equation, so finally what we get? So R equal to, so capital R into L1 by L2 minus 1. So small r equal to capital R into L1 by L2 minus 1. So this is the expression for internal resistance of a given primary cell. So small r, internal resistance of a given primary cell, small r equal to capital R, external resistance of the cell into L1 by L2. So here L1 is the length of the AN1, L2 is the length of the AN2. Okay na? So small r equal to capital R into L1 by L2 minus 1. So finally we get the equation for internal resistance of the given cell. So this is the method of calculating the internal resistance of the given cell, given primary cell, using the potentiometer, using the potentiometer. So is it clear everybody? So this question is same like as the previous one. Compare the EMFs of the two cells, but a small change is here. First we can write EMF, second we can write V. Why? Because first the cell does not connect it into the circuit, so that's why it has maximum potential difference. That maximum potential difference is called EMF. But secondly, the cell lost some current to the circuit, so that's why there is no maximum potential difference between the two terminals of the cell. So that's why we called it as only potential. The cell has only potential. So that's why here we can write V. In place of E we can write V. So E equal phi L1, V equal phi L2. But E and V values from the Ohm's law, we can substitute these values in this equation. Finally we get the expression small r equal to capital R into L1 by L2 minus 1. So this is the expression for internal resistance of a given cell. Okay, is it clear everybody? So thank you very much. This is Kranthi signing off.